All right, guys, thanks for coming. Thank you to the person that canceled for letting me, for creating a spot. I was in DC visiting some family. I'm actually from Chicago. My sister is a lawyer. She moved east to her Silicon Valley, and I moved west to my Silicon Valley. So I'm in San Francisco. I've got this fun talk I've been doing. I've been in the Spark world for quite some time, the last few years. I worked with Databricks. Before that was NumFOCUS as part of the IBM Spark Tech Center for a little bit. Also helped jumpstart that program. And now I had left actually I think it was last July. Yeah, I think it was July 1st, something like that, to start Pipeline.io, sometimes called Pipeline AI, Pipeline ML. I have all the domains, so everyone just kind of, like, depending on which conference I go to, I change it. But for full disclosure, I've been a Java Scala guy for pretty much my entire life. Before that, C. And I was a little skeptical when I got into Python a couple years ago via like data science. And I always, I would always talk about the GIL and all the negative things about Python. And then finally, I realized how much C is actually involved. And when you start dealing with the scientific Python libraries, there's like quite a bit going on there that's super optimized and like really fun to study. So at Pipeline, just a quick plug, what we do, we actually are focused on the end of the pipeline, or sort of continuous pipelines, meaning when you create your models, either TensorFlow, Spark, Scikit, R, whatever, this is the ability to actually push them out and serve them, right? So like you'll hear me talk about model serving, and put it behind a REST API, put it behind a like Kafka stream, right? And then do the predictions, and then put the predictions onto a second Kafka stream, and then that goes wherever it needs to go. So most of the tools that you've probably heard about this week have the notebooks and people, right, like train the model, right? But then what do you do with it, right? So one thing I learned at like Netflix, for example, was to sort of break down barriers and treat data scientists, or back in like 2010, I was on the streaming engineering team, and I was given this freedom and kind of full responsibility to push things out into production. And that's scary, right? Like when I talk to different data science managers and different researchers, and especially the ops guys, do not want people really touching like production. So it's a cultural shift, and some people kind of reject it. Those are the customers I don't work with, but it's more the progressive customers and teams within larger companies that are just tired of that sort of handed over the wall. Take my R model, and this person has to implement it, which is the worst job in the world, and then push it out. And that data scientist, right, like loses insight and doesn't, right, like have any insight into how the model is actually doing in production. So right, like having seen this sort of cultural shift myself at like Netflix, and I could push code out, I can go to the dashboards, I can create my own dashboards, I could look at my predictive performance also. So I can actually have two different models running, one built in TensorFlow, one built in Scikit. They're both doing the exact same thing, right? Like which one is faster, which one uses less memory, and I can actually plot them and see, right, like how close they are in terms of like predictive performance, right? So think of this common use case comes up where people have a classification like algorithm or model. They have the current one that's running. They want to just push out, right, like one small instance of the other one, right? Just a canary is the term. And they want some sort of dashboard that they can see, is this new canary, right, like always predicting the wrong thing, right, like relative to the existing 1,000 instances that are out there that are serving the current model. So it's a pretty interesting space, and it's been fun to work with a lot of people, working with a couple people up here in Seattle also. So yeah, I think I mentioned Netflix, I mentioned Databricks. I was a field engineer there, worked with quite a lot of customers to get Spark up and running, and the same thing, people use Databricks Notebook, they train a model, they want something to do with it. So, and yeah. Let's see, I also run this Advanced Spark TensorFlow meetup. I've spoken up here at the Spark meetups up here. Yes, I'm sure, right, like everyone here knows Denny Lee and Felix Chung and those guys. They're buddies of mine. They might be here, I can't even see you. But yeah, if you want to join this meetup, I don't have a chapter here in Seattle. I think you guys have enough meetups and enough spam, so I'll spare you that. But if you do want to join the San Francisco one, we post all of our stuff, the videos, the slides, in the comments, and you can go to YouTube and find the channel and see all the archives. We're starting to do a lot more AI stuff and a lot of GPUs. The next couple meetups are all AI. The next one I think is July 18th, where we're comparing Keras with PyTorch. So down in the Bay Area, PyTorch is blowing up. Seeing a little bit of the MXNet stuff. It's kind of like men's field hockey or like women's basketball, something like that. I can't really pay attention to all these different technologies. I kind of like certain sports, for example, and I kind of glommed onto TensorFlow because I like the patterns that were coming out, especially distribution patterns. So those are the things that this meetup focuses on. But we do have a speaker coming in on July 18th down in San Francisco. We're going to live stream it. We're going to do all that stuff. It's the same time zone, so it works out for you guys. Yeah, so you guys, so just quick context. This is about 70 slides, and it's typically a 4-hour workshop. I've stripped all the hands-on stuff, obviously, for here, but I've got screenshots of kind of the output, the key output that you would be doing through the workshop. So if you go to Pipeline.io, there's links out there. I think the next workshop is actually tomorrow. Because I was in DC and I was supposed to be there the whole week. I had planned it for 9 a.m. on the East Coast. So unfortunately, I have to wake up tomorrow. I have to fly to San Francisco tonight, wake up tomorrow at 5, get all the servers spun up, and do the workshop our time at 6 a.m. But if you guys want to sign up, shoot me an email. I can get you in there for free or cheap or whatever. I still have to pay for the GPU instances, but it's not that much. Okay, so I'm going to try to do 4 hours in what's now probably 30 minutes left here, but I've done it before. I'll do it again. All these slides are going to get posted. I'll post them to my slide share again. It's all accessible off Pipeline.io. Okay, so from here on out, it's the content. I'm going to talk 50% about training optimizations. This is a talk about trying to optimize your models for performance in production. And by production, if you talk to different people, production means something different. If you talk to data scientists that are trying to build a model, like their production might be moving it off of their sample data that's on their single laptop and then moving it to like an S3 bucket or some sort of larger data set. So to me, that's not production. That's still batch, that's still offline. To me, production, because of my services background, is actually putting this in front of customers, right? And sort of in real time, like scoring these things, like we also do online training as well. If you're familiar with the scikit partial fit, so certain linear models, with partial fit, like you're not fitting and stopping, you're sort of continuously fitting, right? So check out partial fit if you haven't seen it. So we do some of that stuff as well too. We wrap these services, of course, in circuit breakers and all the good Netflix open source patterns that are out there. The architectural patterns, fallbacks. You can't physically deploy your model unless you provide a fallback, and that's the case where possibly the model is taking longer to score. If it's going above 50 milliseconds, you have to put a fallback in there that'll trip the circuit and then send back, just some kind of pre-canned like JSON. Maybe if you're doing recommendations, it would be the top 10 videos, right? It's not personalized to you, but it's kind of a global top 10. That way, like these devices and these callers in, or this, like Kafka stream can continue going and not back things up. And then the second half will be the deployment or the inference optimizations, the serving optimizations, right? That term inference is a fancy way in these neural networks to say prediction. Why do we focus on the inference? Again, it's my personal interest. I think it's more exciting. It's more real time, right? But also think about the number of users that are actually being, or that are on this prediction path, right? This user request path. This is all of the users of your app, right? These are search results. These are, the A/B test, things like that. with training, it's, to me, it's kind of boring. It's batch. The number of users is the number of people in your data science group, which could be, 35 people, could be 100 people. But so the sort of big O on this is much, much larger. People, and the sort of real-time requirements are more like interesting on like the inference side of things. So for this, we're going to use pretty simple models. We're just going to do linear regression, right? Like everyone here understands it. You've all done y equals mx plus b. This is where all the code lives. This is the exact same Docker image that we used for the workshop. We put them on a GPU, and yeah, so you guys can grab all the code. One thing people do find a lot of benefit is going and looking at the actual Docker files. A lot of the tools that we use here for like this talk for the workshop is going to require that you build TensorFlow from source. And doing that, especially with the GPU, it takes weeks and weeks and weeks if it's the first time you're going to do it. Yeah, so just getting CUDA installed on a, like the Amazon P2 instance or the Azure instances is a huge pain in the butt. And then from there, then you have to get TensorFlow to work, and then you have to compile all of TensorFlow. And yes, I'm going to surface some tools within TensorFlow that not a lot of people know about. Some of these tools are starting to make their way into sort of the visual tools like TensorBoard and things like that. But for right now, there's quite a bit of it that's not even Python. It's just literally C++ code that gets compiled, and then you can run it as a script once it's compiled. But and if you compile from scratch on a P2 instance, right, like single GPU, it takes about 6 hours. So yeah, like you can imagine, I would do this overnight, or I would wake up in the middle of the night and see if it failed and have to kick it off just so I can get the image ready for the next morning, things like that. Okay, so we're going to cover quite a bit. We're going to inspect and talk about kind of what a model is in TensorFlow. We'll talk about some training and then prediction best practices. We'll talk a little bit about distributed TensorFlow, which actually is the whole key to TensorFlow, right? Like a lot of people don't like know this or like think about this or rather hear this, but when Google designs anything, they're designing it at scale. It's never just a single node. And so this actually was a bit confusing because when TensorFlow first released, or when Google first released TensorFlow, it was for one single node, right? So there was no distributed TensorFlow until about 3 or 4 months later. And that was more of a technical challenge. Distributed TensorFlow relies on gRPC and protobuf. I believe at the time gRPC wasn't at a 1.0 release, or there was some sort of mismatch between what they were using internally and what was exposed. So they couldn't expose TensorFlow distributed until they firmed up that like gRPC, and then were also able to take the open source gRPC and then roll it back into their own systems, yeah, sort of internally. So because of some of these dependency like issues, and they couldn't actually release the real power of TensorFlow. So this is why when you first heard about TensorFlow and people started to compare it to Caffe and to Torch, and the performance was crappy and blah, 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 it's because TensorFlow wasn't optimized for the single node. Right. So since then, they fixed things. Like some of the obvious things was the like auto differentiation. Right. That's part of the whole gradient. Right. It's part of the gradient calculations. Things like that. Right. Like partial derivatives. Some of that was being done in Python, and they quickly rewrote that and made it C++. And then that had huge gains. But right. Like they weren't really thinking about that stuff. They were more focused on trying to get distributed TensorFlow because that's where things can scale, and really that's where the true power comes. So we'll talk about ways to use queues within TensorFlow. This is something not a lot of people know about. If you're just using simple samples, like you're probably using feed_dict, and that's a way to get data in. It's typically through a Python notebook, right, like an IPython notebook, Jupyter notebook, and you just create sort of like a NumPy array, and then pass it in through this feed_dict thing. It's the absolute slowest way to do training. There's Python to C++ serialization happening. Right, like some of you might like remember the days of Spark when PySpark had to like serialize things between Python and the JVM. So we'll talk about queues and sort of TensorFlow's current state of pipelines, right, like data pipelines and specifically training pipelines. What you'll see is And I think there's been a couple talks here these past few days where Spark is, and like specifically tensor frames. Yes, if anyone, I missed it because I didn't even know I was speaking here until Wednesday. But these tensor frames, for example, kind of are making Spark closer to TensorFlow. And TensorFlow is now starting to become more like Spark with more data set APIs and these queues. And queues actually represent more of a pipeline. Queue is kind of an unfortunate name. Right, like don't think of it, well, it physically is a queue like we think about in computer science, but it's meant to be sort of a, one step inside of these training like data pipelines, ETL pipelines. We'll talk about the XLA, which is the Accelerated Linear Algebra Library. This is experimental. This will become turned on by default. If you guys know Spark, there was that Project Tungsten, started a couple years ago, a couple releases ago, firmed up in Spark 2.0, where they're actually able to fuse together, maps and filters. You would do that before the join, right? Because you don't want to join, right, like more data if you can filter, right, like beforehand. So similar to Spark, right, like TensorFlow builds up this graph. It's not necessarily joins and sorts and shuffle and right, like things for sort of data movement. It's more for like numerical graphs, right, like numerical processing graphs. So you would have matrix multiplies and adds and things like that. So if you guys remember reverse Polish notation, right, like things like that. That's where a lot of these things like come into play. And so the XLA framework gives you ways to traverse that graph, to fuse together operators, to do constant folding, to sort of simplify the graph. And it's the exact same reason why Project Tungsten was created. What you're trying to do is minimize the amount of right, like data movements, right, like in and out of the like L1 caches, from like main memory into the L1 cache and the L0 cache and into the registers. And if you have lots of separate like operations, that data has to keep moving in and then moving off and then in and off as instructions keep swapping around and the threads keep like doing all their fun threading stuff, the interleaving and that kind of thing. So if you can actually create one function, which is what the second generation Project Tungsten for Spark does, it will actually break apart. It sees your logical plan, right, like which is what you're actually doing when you're writing the app, and saying map and filter and join. It's gonna take that specific AST and physically compile Java code, right? It like physically like generates source code. So it like literally looks like Java source code that's been right, like sort of automatically generated. Goes through this compiler called Genino that right, like uses the Apache Commons compiler and right, like some other stuff like that, and can physically generate bytecode. And then Spark actually caches that bytecode so that the next call in that has those same properties can actually reuse the bytecode. And there's huge performance gains if you have one physical function, because that data comes in once, it gets ripped through, and then can then right, like clear out. So it's an instant 10x gain right there. So this is what the XLA is all about. The XLA, if you think of it like LLVM, if you guys know anything about that, it's another sort of intermediate representation. Right, like this XLA stuff has its own operators and fusing operators, constant folding operators, and so this is during training. It's seeing what's going on and can actually fuse things together at training time. The next one is this AOT. This is the ahead of time compiler. This is also based on the XLA framework, which is sort of these like fusing operations, things like that. What's cool about this AOT is that, and so from that fourth to the last bullet point down, this is all going to be optimizations that are done on the model post-training. So the model's been trained, it's sitting there. It's super bloated, right, because it has batch normalization operators in there, and it's got log summaries, where it's like logging the statistics while it's training, and it's got things that are not needed, right, like when you actually go to do the prediction. And if you can simplify the actual prediction path, which is just a forward propagation through your network, right, like when you're training, there's forward prop, it's comparing to the answer key, right, the label, then it's backpropping, it's doing those partial derivatives to figure out which weights, right, like should change and like by how much, you know, if it's positive, negative, that kind of thing. Yes, all that stuff goes away, and it's just forward prop. So there's some optimizations you can do. Some of these are so some of these are being built into TensorFlow itself, so that like when you save the model, it's going to do some of the obvious things, but there's kind of domain-specific optimizations that you could do also that we'll talk about. There's this other thing called the graph transform tool, which is kind of a brute force way to go in if you really know what you're doing, and if you can look at the graph, and I have images of the graph right after it's trained with all the bloat, and then we go through and we can strip out nodes sort of individually, right? So that's a way to make that model smaller, make the forward prop quicker. We're going to do things like the 8-bit quantization, where you sort of look at all the weights after they've been trained, right? Like all those variables, all those parameters that you've trained. If you can sort of plot them and then squeeze them into an 8-bit representation, this makes these matrix multiplies a lot faster, can like reduce your physical model size stored on disk, right, like down by 1/3, right? So now these models can actually fit into small devices, not phones. Phones are huge these days, relative, right? In terms of like memory and storage and flash storage and that kind of thing. But right, like down to the, you know, from if you can get down to like 600K and things like that, then it fits on cameras, then it fits on, you know, some of these really, really tiny devices, which is huge. So with the AOT, for example, which, yeah, I'll show you guys a picture here in a bit. So I talked about the AOT, I jumped to the graph transform. Now I just want to mention one more thing about the AOT. What you do is you point the AOT binary, you know, there's this thing called TF compile, which is built for you when you build like TensorFlow from source. If you have this huge graph, you tell it the graph, you tell it where to start and then where to end. And this AOT compiler can actually go through and pull in, right, like just the bare minimum runtime from TensorFlow, from your operating system, from your NVIDIA, right, like instruction set, and the like end result is one super tiny like binary that can then get shipped out. So you don't need the full runtime for TensorFlow, which is 40 or 50 meg. It's not that much, but if, you know, I've seen models go from what would normally be about 80 meg, you know, with the like 40 meg TensorFlow, and it can go down to like 600K, right, like 500K. So this is huge. And, you know, this is sort of domain-specific things. This is, it's sort of bypassing all those other nodes. And yes, I'll show you guys an example here in a sec. The last few we probably won't have too much time for, but I do want to mention TensorFlow serving and some of its knobs, right, that you can turn. TensorFlow serving, right now what like a lot of people do is they build a model in Scikit or just straight up Python. They pickle it, they put it behind a Flask app, they start up the Flask app, and then, right, yeah, so who knows what happens after that. And so one of the things Pipeline does is we put metrics around there and all that stuff. But so with TensorFlow, TensorFlow serving is a first-class citizen, and like this was actually released with TensorFlow, right, like day one. So this actually came before like distributed TensorFlow. But now this is more for the serving side. So this is a C++ fully optimized, right, like process that can see your graph, and you tell it which inputs, which outputs, and so it can handle model versioning. If you push out different models, it could actually serve both models at the same time. Yeah, there's some other tricks we'll talk about here in a sec. It'll do request batching, so it can take multiple requests from really different people throughout the world. If they end up in physically this same TensorFlow serving process, TensorFlow serving will actually wait, 50 milliseconds or 10 milliseconds or right, like 100 microseconds, some sort of batch window that you configure. It'll take right, like all of those requests, batch them up into one big, huge matrix, because that's essentially what's going on when you're doing forward prop. You're just doing a bunch of matrix multiplies, and sort of put all of the smaller matrix multiplies edge to edge. If you think of it sort of logically as just kind of zero padding everything else, it'll pass it in, and this is going to have huge gains if you're using GPUs, because it's going to pass all that in once to the GPU. That GPU does one big big matrix calculation, which is actually multiple requests from like different people, comes back and then can slice out the result and send it back to each individual caller. So that's when you have scenarios where there's really high throughput. If you have lower throughput and you're more concerned about single request latency, then you wouldn't want to use this because you would automatically incur that, right, like 50 millisecond, you know, because TensorFlow serving is trying to batch things up into that 50 millisecond window. All right, so real quick, I'm probably gonna blaze through this stuff. TensorFlow with GPUs, this is a huge pain in the ass, especially with Docker. If you're trying to run everything with Docker, which is just a given these days, it's, you know, it's just like talking about Linux or Kafka, right? Like everyone uses it, especially with Kubernetes. So not until Kubernetes 1.7, which just came out like a week ago, could you actually, right, like get this working smoothly. There's been a ton of hacks out there, people trying to get this to work. I believe Mesos now has good GPU support as of a couple months ago. That was a huge thing for them. They spent a lot of engineering effort on that. I've actually never used Mesos in production. It's one of those technologies for me. I tried to get it to work on my laptop and it didn't work. I tried to get it to work inside of an Ubuntu cloud server, didn't work. I was getting all these weird lib errors and just kind of gave up and switched over to like Kubernetes, which Kubernetes had, you know, like its own challenges, but it was kind of a little bit easier. I wasn't running into as many dead ends when I was, you know, Googling around for issues. I was able to very quickly get through some of the issues, whereas with Mesos, I found a lot of support, like cases where it was just a dead end and no one could really help out. So yeah, so definitely check out Pipeline.io. There's links to the GitHub. There's links to the like Docker Hub. You can pull these things down, get them going right away. You can like get the whole workshop going too if you follow the steps.
Do you have public images that we can download?
Yeah. Yeah, just go to Pipeline.io. Yeah, all the images are there. There's a section, GPUs and performance, I think, in the left, and follow that, and there's public. It's more than just the like Docker images. I'm very proud of this. It's actually the instructions on how to install CUDA. So once you actually get the P2, that like P2 instance, it still doesn't have all the stuff that you need to get TensorFlow running, right? To get, there's something called the NVIDIA-Docker. That's this bridge that like the NVIDIA folks built and maintained that exposes, that pokes a hole through your like Docker container down into the actual physical devices, right, which are these GPUs. This used to be a huge pain in the ass before the NVIDIA Docker, which is only on a 1.01 release, so it's actually, you know, just about, I think, 8 or 9 months old. But yeah, they recognized the need that people were having problems getting GPUs to work within Docker, and they pounced all over that. So this is in the context of GPUs with TensorFlow specifically. There's this concept of half precision. Half precision these days, especially in these like neural networks where things are fuzzy, right? Like the math can be a little bit off, that's fine. It's more about getting through like data sets quickly. So with half precision, for example, there's this weird fly up here. With half precision, so typically when you're training, or if you're doing forward propagation for the scoring or the predicting, you're dealing with the full floating point 32, right? And so this is very precise. And the thing is that you don't necessarily need this kind of precision. You would rather get through this data quickly to see if you're even close, right? Or if your particular hyperparameters, which if you think of a model graph, right, the actual like architecture of your neural network as a hyperparameter, right? So this is very important. So you can, it's not just tuning sort of learning rate and, you know, like some of the obvious things that people talk about. It's actually tuning where am I doing this particular matrix multiplier, right? Like which node talks to which node and things like that. So people just want to like blaze through this data. And so with floating point 16, for example, which is half precision, this is now supported like natively. Well, actually, I should say that carefully. It's not natively supported just yet by GPUs, but they do this trick where they put in 2 floating point 16s inside of a floating point 32 base core. And there's 4,000 or 5,000 of these cores on these GPUs. And they can basically do do 2 calculations at once, right, on 2 floating point 16s. So you see here the numbers with floating point 16, going from single precision or sort of full precision, you get about 10 teraflops per second. Just by switching to floating point 16, you then double it, right? So it's 21, or really 20 teraflops per second. That came with the P100, the Pascal P100. This is the NVIDIA terminology for these things, the product names. And that was in 2016. I just went to the GPU Tech Conference there, where they released the Volta V100 in San Jose just a couple months ago. Yeah, by the way, if you're looking for a really, really good scientific conference and it's butt-ass expensive, it's butt-ass, it's crazy expensive. It's like the most expensive conference in the world. It's like $3,500, something like that. That is the best conference in if you really want to expand your mind and your, see lots of scientific things going on. There's tons of academic there's like 12 tracks. And when I first went, I thought it was going to be just a bunch of gamers, talking about texture rendering and things like that. It's totally not the case. There's, like 2 or 3 sort of deep learning and self-driving car. There's a whole track for self-driving cars, right? It's just like one talk after another, and just a lot of the research going on. And if you're, looking to sort of get into AI, if you're looking to start a company in AI and get fundraising, for example, one little trick that I actually just learned this is all of these VCs come to that conference. They don't bother anymore with these big data conferences. They don't bother with Strata. They don't bother, with just sort of stuff that was hip a couple years ago. They're looking into the AI stuff. So they're showing up at like the O'Reilly AI conference, which was just last week in New York. There's another one in San Francisco in a few months. I would highly recommend going to. Oh yeah, also I should plug, there's this Jupyter conference coming up by the O'Reilly guys. It's called JupyterCon. For some reason, I'm so excited about this conference. Just like reading all the talks, it's ways to, hack Jupyter Hub or Jupyter and just a lot of, I'm hoping someone's finally going to have GitHub support. I'm just waiting for that talk to show up. I don't think it's there yet, but someone, yeah, so, and that one's in New York, I think, in like September. So it's kind of far, but it's a good one. Okay, so that's the trick there. TensorFlow does take advantage of half precision. I think I'm going to skip this. This is just, one quick thing about this new Volta V100 that was not there in the current generation P100 is these tensor cores. So you've probably heard about TPUs, right? Like everyone goes crazy for the Google TPUs. They just want to know everything. And I don't have a whole lot of information on them. There's papers that have been released. No one can get access to them unless you're a Google Cloud person and unless you've been or you've been sort of specially blessed to get access to them. They're the sort of the really high level way to say it is they are optimized for the forward propagation, for the scoring. So that was more true with the first generation TPUs, second generation TPUs, and these like tensor cores that are built into the V100 can actually help out on the like back propagation and the like gradient calculations and things like that as well. The NVIDIA folks realizing TPUs were big, or this was just the natural evolution of their product, put in about 700 of these into the latest V100, which I think drops Q3 of this year. So keep an eye on that. Right, like the other cool thing about the V100 is with the P100, you had access either to the sort of consumer version, which goes into your gaming machine, which has to be liquid cooled and all that stuff, or you had access to the $140,000 data center version, which has to go in data center, has to have tons of power and all that stuff. The Volta V100, they now have a version, sort of a middle tier version, that's a cool 70,000. So if you guys have 70 grand, yeah, so Father's Day just passed, Mother's Day just passed, maybe it's not. But yeah, I guess Christmas is coming, something, yeah, so that'd be a good one there. Okay, I'm going to skip this. The big thing with CUDA 9, if you've done any CUDA programming, it's the most barbaric thing in the world. It like reminds you of 8th grade, like Pascal or right, like whatever. It's just horrible. With CUDA 9, you now have more sort of familiar thread synchronization semantics. You know, if you've ever gone for an interview and you were, you know, like reading Java concurrency in practice. Yeah, how much time do we get? I have 2 minutes? Oh my God. Yeah, we have 60 slides. All right, streams. CUDA streams, very important. This is how you, TensorFlow takes advantage of data coming. It can process data at the same time that data is coming from the CPU. This is very important. It came in about CUDA 5 or 6. I think this is TensorFlow basics. Let me see here. One thing to point out, there is this TensorFlow Hadoop sort of ecosystem project that the Google guys have created. This is what you would put in your Spark app at the end of your data pipeline, your sort of ETL pipeline. You would create what's called TF records. If you're familiar with Hadoop, it's kind of like a sequence file. It's just, you know, like another file format that TensorFlow likes. So if you really want to get super fancy with your pipelines into TensorFlow, you can tack this on. You know, these are the Maven coordinates, and you can then from TensorFlow, yeah, because TensorFlow talks to like HDFS now, which is really cool. So use queues. Queues are very efficient. Queues use these streams, right? So they take advantage of the CUDA streams so that you can process and keep these GPUs fully saturated, which has always been a problem. Here's ways, so TensorFlow model. Oh yeah, keep in mind that like TensorFlow, when someone says TensorFlow model, like you really have to understand, are they talking about the graph, which is static, or are they talking about the learned variables? These things travel separately, and that's on purpose. That way, your graph stays static if you choose to start from someone else's checkpoint, right? Like that's what the term checkpoint is. It's kind of a frozen state in time of these variables. You can actually pick up that model, load that model, pull in someone else's, right, like checkpoint variables, and then pass your data in and start to train and build off of those. So, right, like these neural networks are sort of always ready to be retrained, okay? That's not optimal for the prediction side, which I'll show in which I probably won't show, but it's gonna actually freeze at like prediction time, it's going to freeze those mutable variables into the graph as constants, right? And then push that out behind the REST API, and then it's just doing forward prop, because there's no more training. Like when you freeze, you actually create a separate sort of entity that then gets deployed. You can, right, like maintain this, you know, sort of TensorFlow model and keep training, and then you just freeze again and push it out. If you don't know about batch normalization, you should always be using it, period. There was a talk, I believe, yesterday. This helps with vanishing gradients. This helps, you know, if you're doing a lot of multiplies on very small numbers, which typically you're doing here, like eventually those are going to end up really close to 0 and when you lose precision. Okay, so that paper came out in 2015. Check that out, it's pretty new. Distributed TensorFlow. It's pretty important. So all you have to know here is you write the graph as though it's single node and it's not distributed, and TensorFlow will automatically put in the send and receive nodes between physical workers. It's using gRPC and, you know, protobuf beneath the covers. You don't have to worry about that. Let's see. One funny thing is in Spark, there used to be, or there is the concept of a master and a slave. Yes, obviously that's, you know, not very good. And TensorFlow, the Google guys chose chief instead of master. So it's chief and minion. I'm not quite sure how I feel about chief, but anyway, you know, with any distributed system, there's lots of failure points. Okay, XLA. So here's, this is the best way to show it. So right, like before fusing together operators, you have many, many small operators. After you run XLA and TensorFlow realizes it can fuse these together, it's going to create one function. So that's going to give you a lot of gains. Here's just kind of the low-level details. Prediction optimizations. This is that like AOT thing. This is where you'd point it to the graph, feed, and fetch, which is the input and the output, and it'll slurp in everything it needs, bare minimum, to just get you from the feed to the fetch with the graph. Graph transform tool. This is right after training. This is just simple y equals mx plus b. And then this is after we start using the graph transform tool and simplify it down. It goes from 8 billion nodes to 5 nodes. Here's the weight quantization thing I described, where you can plot all the weights that are trained and sort of squeeze them into 8 bits. Makes everything easier, makes the matrix multiplies faster. Activation quantization, out of scope here, but you could read about it in TensorFlow serving. This is really cool. Multi-headed inference. This is the last point I'll make here. You can, instead of treating a neural network as a way to classify something, where you like pass in inputs and it's just going to return if it's a penguin or if it sees a car or whatever, you can actually have it return multiple responses. So one would be the actual like penguin and that classification, but also you can return that last layer, that last softmax layer, and pass that in then to a subsequent model. Right? So this is where you start seeing ensembles and kind of chains of models, kind of a model prediction pipeline. Right? So it's not a training pipeline, but a model prediction pipeline, where it's using these neural networks as a feature engineering like mechanism. Okay.
Good. Yeah. We got time for like 2 questions.
2 questions.
Real
okay.
Quick.
So I'm new to TensorFlow, and one of the problems I normally have when running with the GPU is I overload the GPUs. GPU doesn't have enough memory for me to load a little bit more higher pixel images.
Yeah.
So any advice on how I can divide the workload or slow down the workload, or do kind of lazy loading on the GPU so that I can use.
Yeah. So I skipped the slide. It was queue capacity planning. Yes. So currently, are you using queues to feed the data in? Because with queues, you would define the batch size, and that's exactly what you do. Is you start with how much RAM that your GPU has. Let's say 12 gig, right, which is typical. You look at the average size of your JPEGs, and you just divide that in and figure out what's your batch size. Can I get 25 JPEGs in? Then start with that and tune up and down. But you definitely want to be using queues. Yeah. Queues have this, that concept of a batch size and things. Yeah.